All right, with this, I think we can start. Welcome everyone to this week Autonomy Talks. This week is a pleasure to have Dr. Sandeep Chinchali. I hope I spelled it correctly. So Sandeep is an incoming assistant professor at UT Austin in the departments of electrical engineering and computer science. And prior to doing this, as he was discussing, he graduated from Caltech, where he worked on robotic stuff at NASA Jet Propulsion Laboratory. And he also got a PhD from Stanford University, working with Professor Sachin Katti and Marco Pavone. Notably, he was also a first principal data scientist at Uhana, a Stanford startup, which worked on data-driven optimization of cellular networks, which now has been acquired by VMware. Today, he's going to talk about some of his recent work about collaborative perception and learning between robots and the cloud. And we're all very happy to hear what he's going to tell us. So go ahead, Sandeep, the stage is yours.
Okay, thanks very much for the kind introduction and the opportunity to speak here. So today I'll be discussing my thesis research on cloud robotics, specifically how resource-constrained robots, such as low-power drones, can use cloud computing services to improve their understanding of the physical world. So today we're starting to see fleets of networked robots, ranging from low-power delivery drones to even this Amazon Kiva manufacturing robot pictured in orange. And we're starting to place very high hopes and demands on these robots. So ideally, we want them to be cheap. At the same time, we also want them to be compute and power efficient. But finally, we also want them to be highly autonomous, accurate, and resilient in the physical world. And these demands are starting to be somewhat at odds with the way we're building machine learning systems today. So we're building machine vision models with millions of parameters that are very require dedicated hardware to run, such as power-hungry GPUs and sometimes even tensor processing units. But moreover, they require a lot of human data to label, as well as extensive cloud computing resources to train. So in other words, they're highly accurate, but at the same time, they're very compute, power, and data hungry. And this trend is starting to become untenable for the smallest and most resource-constrained of robots. So a key question that motivates our research is, how do we actually scale? So can we actually build swarms of compute and power-efficient robots that are accurate, but at the same time are efficient enough to scale in different resource-constrained settings? So if we return to this fundamental question of actually how do we scale robotic systems today, if you look at the software industry, software applications have been able to scale tremendously well using centralized or cloud computing resources. So a natural question to ask is whether robots can also benefit from the cloud. So one prime benefit of using the cloud in robotics is to augment real-time perception. So suppose a low-power drone has a modular fault-tolerant neural network for perception, but occasionally it might need help. So it could use a larger deep neural network that is compute and power hungry that might be running in a nearby cell tower in a future 5G wireless deployment. So that's one benefit of using centralized computing services. But also for other robots that are not necessarily resource or power constrained, you can still continually learn and improve computer vision models, say nightly. So it's estimated that a self-driving car will measure more than 4 terabytes of very rich sensory data in just an hour and a half. So this accounts for more than 1.9 million potential images. So if you could say every car in a fleet could potentially only upload the top 10% most interesting images it saw daily to the cloud, how should they automatically select this data in order to do continual fleet learning and improvement of vision models as well as control policies? So though there are some alluring benefits of using the cloud in robotics, they actually come with key systems costs that are typically underappreciated today. So first, our wireless links are highly variable across space and time. So how do we build robots that benefit from the cloud gracefully, but also rely on fault-tolerant modular local computing in case the network times out? But also there's quite a lot of systems costs associated with the cloud. So it takes some time and cost to upload over a network. And it also takes human time to label data and cloud computing resources and costs to improve models. So given the benefits of the cloud, but also these end-to-end systems costs, there are some key decision-making algorithms that need to be made in this field. So the first question of interest is, what data should we actually prioritize to the cloud? So what data should we actually ship in order to maximize the ultimate accuracy of these computer vision models, but also minimize end-to-end systems costs, which start from the network, but actually culminate in human and cloud computing time? So fundamentally, this is a problem of sample selection or collaborative learning, which will be the first part of this talk. And then the second part of this talk, I'll move on to more real-time inference decision-making. So let's say you're successful at crowdsourcing interesting data from the field to train an array of computer vision models. Some might be very resource efficient to run on board a low-power robot, and some today might require an edge computing server to run a larger machine learning model. So in real time, can a robot decide based on its local uncertainty what is the right model to use? So fundamentally, this is a problem of real-time model selection, which I'll get to at the second part of this talk. And a third key question that remains is, how do we actually extract actionable, task-relevant information from very rich video and LiDAR sensory streams that robots see? And this is the subject of my current work, and it's very preliminary. But the idea is, if we co-design the way we represent sensory data with an ultimate machine learning task, ideally we might be able to send much less over the air, but still get the same sensing task accuracy if we optimize for machine perception metrics as opposed to human perception metrics, which are currently used today. So fundamentally, this is a problem of representation selection that I'll touch upon towards the end of this talk. So my long-term research goal is to build algorithms that allow robots to get the best of both local and cloud computing. And there's a lot of prior work in this domain. So there's currently an excellent community that's working on resource-constrained machine learning, such as the TinyML community that's building quantized compressed neural networks that run on edge computing hardware. And this is an example of a talk that was actually recently given at Stanford about TinyML. And there's another school of thought, which is building extremely large neural networks, sometimes that required cloud tensor processing units to run with billions of parameters and billions of training examples. And this was an example of a talk given just 2 days later at Stanford at the same venue. So a natural question to ask is whether robots can dynamically get the best of both worlds. And just to provide some references, there are a lot of people working on energy efficient ML. And at the same time, there's been a lot of historical work on cloud robotics, including from ETH Zurich. Some of the first works on RoboEarth are an example of this. So my research is trying to build these decision-theoretic and flexible decision-making algorithms that allow robots to gracefully trade off the marginal gain in accuracy they can get with the cloud with end-to-end systems costs. And these algorithms I'll discuss in this talk today are somewhat economic in nature. So again, they try to trade off marginal gain with systems costs in a flexible but principled way. And some of these papers were just recently appeared in RSS and ISCR. And they're motivated by some of my prior work. And all the algorithms I'll discuss today have been deployed on low power deep learning accelerators, such as this Google Edge Tensor Processing Unit and these low power NVIDIA Jetson Nano GPUs. So in the first half of this talk, I'll describe preliminary work on collaborative learning, which is, given a large sensory stream, how robots can intelligently sample interesting training data to continually improve their computer vision models. So this concept was tested on my driving data. So I drove around for 6 months in the Silicon Valley and videotaped my commute every day. So a robot might see a well-understood freeway scene that I'm picturing here, or it might chance upon a dynamic construction site that it might not have seen before with new visual concepts such as excavators and traffic cones. Or you actually might see a novel visual concept, such as a self-driving car being tested on the road. So this example actually was crowdsourced from my video data and is not a stock image. So typically what we would do today is we would simply store all this data, upload it all to the cloud, and use extensive cloud computing resources and human time to label this data and retrain a model. But the benefit is that you can compress and quantize this model again to a resource-constrained robot or even your iPhone to enjoy better computer vision performance on the next day if you continually learn from this fleet data. So the key idea I'll be discussing is how you can build an intelligent but lightweight sensor sampling algorithm in Gray that learns to reject these well-understood training scenes, but only harvest the interesting training examples so that robots can quickly learn, but with minimal end-to-end systems cost. So to preview these results, they were tested on 6 months of my commute data and some standard computer vision data sets. This sampling algorithm in Gray is efficient to run on a tensor processing unit, and it reduces the amount of images that a human labels by about 60 to 80%. And in the next part of this talk, I'll transition to collaborative perception. So suppose you're able to crowdsource and train these computer vision models from fleet data, then you can train an array of models, some in blue that can run on these in a modular manner on these low power accelerators, and some today that might require more dedicated hardware to run, such as an edge computing server. And even as the ability of local hardware gets better, there still is a fundamental trade-off between model complexity, so the size and number of layers in a deep neural network, as well as accuracy. So a natural question to ask is, in real time, which model should a robot use? So should a robot use a fast, responsive local compute model, or if it's highly uncertain, should it query a slower but more accurate model on the right? So here we frame this as a model selection problem and a Markov decision process. And I was able to build a lightweight deep RL agent or reinforcement learning model selection policy that allows a resource constrained robot to double its performance in computer vision, but with very minimal overhead. So this selection algorithm in Gray is an RL policy that's very lightweight to run on a commodity GPU. So for this rest of the talk, I'll describe some brief background, and then I'll take a deep dive into collaborative learning and perception, and then touch upon our ideas for co-designing the way we actually represent this data from robots for machine perception tasks. So I alluded to this edge tensor processing unit, or TPU, at the start of this talk. And it's this lightweight accelerator that I'm pointing to here. It consumes about 2 watts of power. A conventional GPU would consume about 200 watts. And you can see on the video on the left, it's very fast for real-time inference. So inference is running at about 70 frames per second. Whereas a couple of years ago, you might be stuck with a generic ARM CPU. It is not dedicated, doesn't have a dedicated ASIC for these neural network inference patterns. So it's an order of magnitude slower. So clearly embedded AI is getting better, but still, there's still a fundamental trade-off between the complexity or the size of a deep neural network and its inference latency. So I showed these images before, but if you look across a very large data set, you see there's some trade-offs. So in the middle column, there's the accuracy of an object detection model. So the metric is the mean average precision, or MAP in blue, which I'm pointing to. And you can see these large models, such as FasterArt CNN, are typically double the accuracy, but at the same time, they have an order of magnitude larger or slower inference time. So a natural question to ask is whether a robot can dynamically get the best of both worlds in real time. And you can actually see these stark trade-offs right from my commute data. So what I'll be showing you is a video of a construction site near Stanford. And what you'll notice or pay attention to is that there's a far off excavator or a tractor. So in the left panel, I'm passing it through a mobile optimized model that can run in my iPhone. It's called MobileNet 2. And on the right, I'm actually post-processing this video using a very slow but accurate deep neural network, FasterArt CNN, that runs in the cloud. And the key takeaway you'll see is that you can actually, it takes MobileNet 10 seconds longer to localize this distant tractor simply because it's myopic. So it needs a close field of view, whereas the cloud grade model on the right can localize it from the get-go. So let's actually watch these videos. So what you can see here is there's quite a lot of flutter, and only as you get very close to this large tractor will MobileNet recognize it. Whereas on the right, you can see that the excavator is stably tracked using a much slower model. So a natural solution might be to first ping this edge computing server to query the slow model, and then track it in real time using your mobile phone. So a natural question to ask is, how can you actually crowdsource this data from the field in an automatic way? So I'll take a deep dive into collaborative learning. So again, the problem becomes, given a very large sensory stream, how can a robot build this intelligent sampling algorithm in Gray that learns to reject well-understood streams and just harvest interesting examples? And it turns out that this is useful for self-driving cars to do collaborative fleet learning, but also it's of interest to even in space. So I've been talking to NASA Jet Propulsion Lab, and I was there at a workshop, and they're planning to actually put up a cloud computing server in deep space. And the idea is that the deep space network has a very poor bandwidth to relay back to Earth. It's about 5 megabits per second. But a lot of space rovers and telescopes need to prioritize data at a central server, perhaps in space, before relaying back to Earth. So the question is, what data should they send back? So the first question of interest is, why should we specialize computer vision models? And why can't we simply just use all field data? So again, this is a picture from my dash cam. And this is a construction site that I've passed through a default pre-trained computer vision model trained on the COCO dataset, or common objects in context. So while this is good for common objects, it doesn't even have the notion of a traffic cone. So pervasively, these traffic cones are mislabeled as people. And on the right is my automatically trained domain-specific model that's specialized to construction sites. You can see that we mitigate these errors, but they actually come with quite a lot of cost. So every image from the field is very expensive. So I actually paid Google to label my commute data. And you can see that a single image has more than 20 bounding boxes. So if you do the numbers to actually pay Google to label your data, it takes quite a lot of human time and cost. But also there are these end-to-end systems costs about how much you upload and how much you train on that I've discussed. So it motivates the need to intelligently select what data we want from the field. But it turns out that this problem is somewhat ill-defined, and it's somewhat hard to actually sample interesting data from the field. So let's take a case study that I will generalize more later. So let's say I'm interested in finding these rare construction sites and more examples from the field, or I want to recognize a rare visual concept, such as self-driving cars being tested on the road. So if you scrape Google Images, you see a very small initial data set of just 200 images initially. So using transfer learning, you can train a nominal computer vision model, but by virtue of having a very small initial data set, it's going to be rather poor initially. You can quantize it and sync it to your mobile phone, but your phone or a resource-constrained robot is actually tasked with rather a hard problem. So given a rare visual concept that might be less than 1% of my commute data and a poor detector, how can you actually automatically sample new images that are task relevant? And it turns out there's an explosion of samples one could take. So given just 15 minutes of video, if I want to select 2,000 most interesting images, turns out there's a combinatorial explosion of possible sets. So it's not at all intuitive how we can automatically crowdsource these new samples. So this typically has been discussed quite a lot in the literature under active learning or novelty detection schemes. And the crux of these methods is they use very complex uncertainty metrics to figure out whether a new image is worthy of caching or is far from a training distribution. So they use an acquisition function that's typically based on distribution on model parameters, such as using a Bayesian deep neural network. But it turns out that some of these are very compute intensive to run on resource constrained hardware. So this is an example of a prototype I built with the Raspberry Pi and a tensor processing unit. And you can see that this TPU on the top, you have to pre-compile just one set of model parameters on a dedicated ASIC, and you can't run a distribution on model parameters. And even if you could in the future, each forward pass of the neural network is rather slow. So you might not want to take many forward passes for the same image just to estimate uncertainty. So by not actually using today's active learning mechanisms, I'll show how we can build a very lightweight sampler. The key idea is to use cloud computing to direct and build a data-driven filter for what's interesting to collect from the edge or from these resource-constrained robots. So now I'll go into a problem formulation for collaborative learning. So on the right panel, which I'm pointing to, you have the robot and then the cloud. And I'll slowly start to build up some notation. And the key crux or problem of interest is how do we design the sampling policy pi in green that I'm pointing to, which is lightweight, can run on a USB stick, and selects interesting images from the field. So formally, a robot might see t images per day I, and it's given a set of target classes, which I'll define soon, and a set of initial images. And the constraint is you can only send a cache limit of images that is much less than what the robot sees daily. And the goal is to find a good sampling policy, pi in green, that maximizes the accuracy of the learned computer vision model after n days of learning. And just by virtue of uploading selected data doesn't mean you have to delete it on board. So you can actually, if you want to re-look at this video, you can store it on board, but may not relay it to the cloud in case the network is a big problem. So the first module of interest is the sensory stream. So we're just calling it an image that a robot sees at day I at time t as xi of t. And the constraint is you can only send n cache daily. And here we're making an assumption that we want to first look for task relevant images. So the general problem of finding anything interesting is a very tough problem to solve. We're solving a subset of this, which is given a subset of a class of data that I know my computer vision model is poor at, say construction sites or Waymo cars in my example, and a few images in a data set D0 or seed images. Can I ask a fleet of robots to source more images for these target sets so that I can continually improve my vision performance on these subset of images? So on each day I, using this nominal data set D0, I can use transfer learning to learn a nominal computer vision model. And it's given by FDNN of I. So it's this blue computer vision model I'm pointing to that maps an image x of t to a nominal set of predictions, such as the bounding boxes, confidences for this target set, and labels. So at this point, we have a computer vision model per day. And the key question of interest is how might I design a nominal sampling policy pi? So pi intuitively should take in the outputs of the computer vision model, y bar. It should know what target set to search for from the field. And it might actually take some hyperparameters data, which I'll subsequently describe, that actually come from the cloud and define a data-driven filter about how to sample these images. And its decision is given by AFT, namely whether to add a new image to the cache or not. And intuitively, you can think of these hyperparameters data in green as guidance on the cloud, from the cloud, about what distinguishes a task relevant image from background irrelevant noise. And I'll make these more clear on the next slide. So the key idea here is you want to efficiently on hardware filter images of interest. And I'll show you a very simple detector that might be able to do so. So the way to abstract this is given a very large vision stream, you might have irrelevant images in blue, and you want to select automatically this interesting image in red. And all you have at your disposal is a quantized neural network that gives you some outputs y bar of t. And you might have some parameters data from the cloud, and you need to decide A of t. And intuitively, I just want to filter the targets in red from background noise in blue. So there are many ways to think about how to do this, but I'll show you a way that's very simple, but can be run on a USB stick. The idea is, as I train my computer vision model, I can calibrate its uncertainty and use that as hyperparameters to store on the robot to distinguish signal from noise. So I'm trying to build a data-driven filter. So let's focus on the leftmost panel. On the x-axis, I have embedding distances, and embeddings are compact visual descriptors that come from the middle of a neural network. And typically you see that embeddings between two classes of same objects in blue have a lower L2 norm distance or cosine distance than two objects outside of class in red. So this is one proxy metric to describe whether an image in red is potentially different from what you have seen before. And you can find this empirical cutoff given by rho threshold, where rho is the embedding distance, as you train your neural network and send this value rho to the robot. And of course, this is not a perfect filter. There's quite a lot of overlap, but you can tune it over time. And if you focus your attention on the right panel, you see a similar bifurcation when you look at softmax confidence scores. So of course, it's well known that softmax confidence scores are not a formal probability measure, and they're susceptible to adversarial examples. But what you can see here is that in general, that there's a bifurcation between target images, so actually images of Waymo cars or construction sites that you're searching for, and irrelevant images in blue, and you can build a coarse proxy threshold or confidence threshold. And of course, there are cases where you might sample irrelevant images, but the way we handle this is we relabel these target images when they're uploaded to the cloud to mitigate these kind of problems. So essentially, when you train the neural network, you can profile what is a data-driven filter between signal in red and noise in blue, and store these two small numbers on a USB stick, which are rough proxies for what to sample. And these are your hyperparameters. So at this point, you can also think of a very simple decision rule. So given these two cutoffs or empirical thresholds, you can say you would cache nominally an image if the confidence for a target class is greater than the data-driven threshold. And similarly, there's another decision rule. If the embedding distance is lower than some threshold, then it's potentially an interesting image to cache. And since you already have run your deep neural network on a resource-constrained accelerator, these lookups are very fast to compare to these thresholds. You can do it actually an order of magnitude faster, in about 0.3 milliseconds on a conventional low-power Raspberry Pi. So at this point, I've discussed a nominal sampling policy, and now it's time to collaborate with the cloud. So there's a way to populate potential interesting images in the cache, and we need some feedback from the cloud. So you can upload these, and the question becomes, can I improve and direct the sampling process for the next day? So every day in my experiments, I uploaded about 200 images only, and I paid Google to label them. And they were uploaded according to this sampling policy. We annotate them and then use standard practices to do a training and validation split. And importantly, every other day, I test it to have a completely different training and testing set. And now there's an interesting question. So given this nominally new data set that has been annotated and the original computer vision model, I can use transfer learning to improve the vision model. And given this new model, can I calibrate uncertainty a little bit better and improve the sampling process? So now we have a new computer vision model. We're going to sync it to the robot. And in this step, which is a key step, I can improve the data-driven filter. And the key insight here is you want to delegate compute-heavy tasks of retraining models and calibrating uncertainty to the cloud and do the sampling at the edge. So on the left, I'm showing you the results from day 0. So on day 0, there might be quite a lot of uncertainty about what distinguishes a task-relevant image in red, such as a construction site or a Waymo car, from background irrelevant noise in blue. So your sampling threshold or confidence level might be rather conservative initially, given by the black line I'm pointing to. And then as you continually annotate data and use targeted feedback and improve these models in the cloud, you see you have a much sharper filter. So naturally, you could just adjust this separating line and pass those hyperparameters back to your robot. So at this step, we have a new computer vision model. We've adapted these policies. And the question becomes, what is the final accuracy after n days of learning? So just as a recap for this algorithm, you have a set of task-relevant images, you might want to query more data from the field to improve models, such as computer vision, such as construction sites or Waymo cars. You train a nominal detector locally. Not only do you train this detector, you calibrate its uncertainty using these proxy metrics of embedding distance thresholds and confidence scores and sync it to the robot. These are just two numbers. Then, given a new image you might see in the field, you ask, is this nominally potentially something of a target class? If so, I should cache it. Of course, there are errors that might be made. You use targeted human feedback to correct these and assign a label, and the process repeats. So let's actually see how this works empirically, and then I'll move on to more real-time inference problems. So again, this was tested on about 6 months of my commute data. And the key question of interest or metric of interest is what is the resultant accuracy, which is on the y-axis, over days of learning or rounds on the x-axis. So here I'm showing you many benchmark schemes. So our system in bold orange, which I'm pointing to, is called HarvestNet, because I'm trying to harvest interesting examples from the field. And every scheme I'm showing you is extremely cache limited. So I only upload 200 images daily and pay Google to label them. And these are based on your human labeling costs as well as your network costs. So an Oracle scheme in green is an upper bound solution that perfectly knows what interesting images to upload. And in red is a non-adaptive scheme. So it's not using cloud feedback. And in blue is just common random sampling. You can see that our scheme does fairly well and achieves fairly high accuracy compared to these two benchmarks. And here the difference is much more stark. So these are on learning the dynamics of what is a construction site. These are constantly changing. And you can see that by using very little data and by continually training and retraining these filters in the cloud, our scheme in bold orange does better than non-adaptive schemes that simply just keep these hyperparameters on what is an interesting image fixed across days. So again, this reduces the number of images you sample by between 60 to 80% and reduces these end-to-end systems costs. And just to show that these just generalize past road scene domains, here's another common data set, FaceNet, to recognize different faces that you might see in a lab environment from a mobile robot. And here the decision rule is actually using embedding distances, and you can see very similar behavior for our system in yellow. So this is a fairly general algorithm. And at the end, once you crowdsource this data from the field, you can actually train quantized computer vision models that run on a tensor processing unit, but also larger models that today might require dedicated hardware. So a natural question is during real-time inference, which model should one use? So this brings me towards a sort of problem on collaborative perception and real-time model selection that I'll go through a little more quickly in this part of the talk. So now I'll actually pause to see if anybody has any questions. I'm happy to take any questions. Hello? Am I?
Yes,
okay?
yes. If somebody has questions, feel free to unmute yourself.
I can also take questions at the end. That's fine.
Yeah.
No question at this point.
Okay, sure. So this was mostly just systems building, and this has a little bit more math. So this is a problem of real-time collaborative perception that I've described. So can we build a lightweight selection algorithm in gray that decides at every time point whether a robot should use a fast responsive local compute model or a larger vision model when it's uncertain? Okay. And so the way we'll cast this as will be a Markov decision problem, and specifically a decision-making problem under uncertainty. So let's actually see why this formalism might be fitting. So let's say you have a robot on the manufacturing floor. To keep the compute costs low and power costs low, you might have a very small detector. It's seeing a stream of video that has temporal coherence. So on board, it might have a very small neural network that's power efficient. And there might be a central warehouse server where you can run a larger vision model. Or you might actually be able to ask a human for help. But this human abstractly has limited bandwidth to respond to queries. And similarly, this server model. So you could say that you have a query budget. Every robot can only query a human, say 5% of the time, or query this complex model, and 5% of the time. So given this query budget, as well as uncertainty about what a robot might see in the future, as well as the potential accuracy benefit of this larger model, it needs to make a decision about what is the appropriate model to invoke in real time. And you can cast this as an optimal control problem where you want to balance prediction accuracy, but also minimize the cost of querying model. And here you can formalize this as building a decision-making algorithm or a policy, or the selection algorithm in gray, that splices between two sources of compute. And what you can see and exploit here is there's quite a lot of temporal coherence in video. So between two successive frames, I'm actually taking the difference between them. So most of the background is actually black because not much is changing. So ideally, at the start, you should use your fast local model. And then if nothing has changed, your selection algorithm should learn to use past predictions. And only if you're highly uncertain and the video has changed a lot, should you use a complex model. So how can we actually build a model-based selection policy? So the action space here is you potentially want to use past predictions to exploit the temporal coherence in video, use the fast model or the slow model. And the constraint is you might have a query budget set on your network bandwidth or human bandwidth. And the state space informally is whether you can use past predictions cached in memory, how many queries you have left to this complex decision-making model, and potentially what are the statistics of a new image you might see in the field. And the dynamics of this problem are unfortunately somewhat hard to quantify analytically. So you want to know what the marginal benefit in terms of accuracy is of using the larger model and what a robot might see in the future, which is hard to predict. And since it's hard to, ideally you'd want to use a model-based model selection policy, but since it's very hard to model the dynamics of what a robot might see, we're looking at learning-based selection policies, specifically reinforcement learning. So many of you are familiar with DeepRL, but just as a primer, your agent in this case is a model selection algorithm running on a robot's GPU. The action is which current model or neural network to invoke. And the environment might be what a robot might see in the future, which is a function of its mobility and external agents. So what's interesting here is that RL tends to work well in cases where there's an exploration and exploitation trade-off. And it's actually inherently baked into this problem. You want to exploit the fast model as much as possible. But at the same time, you want to not miss out on the potential accuracy gains of a more complex neural network. You can't analytically determine this, but you might be able to actually learn this through interaction or through an offline data set. Again, it's hard to model the dynamics of the system, so we're looking at RL. So the crux of this is actually a computer systems approach, which is how can you actually build a model selection policy that will run with very low overhead on a commodity GPU. So the goal is to build a selection algorithm in gray. And I'll start to show the state space and how we can design one. So the action space is you might have the local prediction that you can use, a modular model in case the network times out in blue, or a larger model in green. And a key question of interest is what should be the inputs to this decision-making algorithm? So what is state? Potentially, should I add a new image directly to the decision-making policy? But it turns out that control or even selection or resource allocation from the pixel space is very hard. So I'll show some systems insights that allow us to build a very lightweight selector that can run on hardware. So the first insight, as I've shown before, is that there's a lot of temporal coherence in video. So you can simply use past predictions that are cached in memory, and that is one of the decision-making actions that is available to your selection policy. So with action 0, you can query a local model. Action 1, query a larger model, either on device or at another server. And with action 2, you can query past predictions cached in memory. But still, the question is, what should be the sensory input to this decision-making algorithm? And here, we're actually exploiting these dedicated hardware blocks that can quickly look at motion vectors and take the difference between 2 frames of video and actually sum these pixel differences, which are a coarse proxy for how much the video is changing over time. And that is another input to this selection policy. So you're sidestepping predicting what a new image is and using temporal correlations from the past in order to guide what model to invoke. So again, starting from this somewhat abstract block diagram, you can actually add in these systems insights to build a selection policy in gray that is actually 18 times smaller than even these small quantized neural networks, which makes it efficient to run on hardware. So actually, you can formalize this as a model selection Markov decision process. And most of the formalism is in our RSS paper. But essentially, you have a fast decision-making model and a slow decision-making model. Without loss of generality, they can be on the same device or at different devices. And they need not be deep neural networks. And they're modular in case the network times out. And your performance criterion is you want to maximize accuracy, but at the same time, minimize compute costs. And you can actually tell these compute costs directly from experiment. I showed you this table before. You can see there's a trade-off between the accuracy of a deep neural network and the inference latency. So you might say the cost of using the larger model is 10 times more than the small model because it's 10 times slower to run. So let's actually see how this works on commodity hardware. So the first question of interest is, how do I actually train this model selection agent? So here we're using some simulation to real transfer algorithm. And the general idea is I can train collect some nominal training data from an actual robot. And this video, as you drive it around the lab, will have some coherence time. So some faces might show up for some time, and then with some coherence pattern, then it might transition to a new face. So I actually can create a lot of synthetic time series using these coherence patterns that I've observed from the field. And you can abstract it as just a sequence of frames. And offline for each frame, you can pass it through a fast neural network and a slow neural network and quantify the difference in accuracy offline. And you can build a simulation algorithm and train your RL agent in parallel and deploy it and fine tune it on actual hardware, which is what we did. So this is our key experimental result. And this was actually tested on real wireless links. So the key metric of interest is you want to maximize accuracy, which is on the y-axis, and at the same time minimize offloading or compute costs, which is on your x-axis. So in blue is our RL agent, which is running on a low power hardware platform on a real robot. And in green is an upper bound Oracle solution. This was tested on about 100 trials and different variable network wireless conditions. So in green, the upper bound Oracle perfectly knows what the robot model will output, as well as what the larger deep neural network in the cloud will say. And it perfectly knows what the robot will see a priori. So you can use dynamic programming to figure out this trade-off and figure out the optimal solution in green. And in gray are typical policies you could use today. So you could just use purely local computation and not use the cloud. So notice here the all robot solution has a low cost, but a low accuracy. And in gray here is a heuristic. So you could say I don't need a fancy decision-making model. Potentially, I could just say if the local confidence is lower than some threshold, then I would stick with using the cloud. Otherwise, I would use local compute. But it turns out that this doesn't incorporate the fact that you have a budget. So it doesn't allocate queries to the large model selectively when you're uncertain and learn to back up during other cases. So this is not such a good algorithm, a heuristic. And you could also use an all-cloud approach. So the all-cloud approach has quite a lot of variance. So let's say you can only query the cloud 10% of the time. Maybe every 10th frame you can query the cloud. But here, it doesn't learn to selectively, again, use queries when the robot is most uncertain. And this is what our RL policy is learning in blue. So therefore, achieves a higher accuracy and lower cost. So essentially, you can actually see it from this screen. In cases where it's fairly uncertain, certain locally, it just might be able to seamlessly interleave robot computation with cases where it is uncertain in yellow, and it might require a cloud server, and you can splice these on the same image. So more details on how to actually set up this Markov decision process are in our paper. So now I have about a few more minutes. I'll just describe some very preliminary work. And the key question of interest is most of my research currently has been very systems heavy, just actually building systems. But can we abstract some more general or interesting research principles from this? So a key problem of most of my work that I've done previously is that I'm naively just offloading raw images to the cloud, which are rather large and are designed for human perception. So every pixel matters essentially the same. But in a lot of these automated sensing tasks, especially from IP cameras, as well as sometimes from robots, the ultimate consumer might not actually be a human. A human might not be watching this video, but it might be a deep neural network. And this neural network might be able to sense what's in the image and to classify it using very few pixels. So there's an opportunity to send much less over the air, but still get the same sensing task accuracy. And you want to co-design the representation with the ultimate task. So there are many applications of this, but I'll actually show you some recent results from a preprint. So typically what you would do in information theory or source coding today is given an image x of t here, you would build a custom encoder to a latent representation z, send it over a wireless link, and build a custom decoder to minimize the root mean squared error. So you want to minimize the distortion between x hat and x. And that's where a task agnostic scheme would typically be used today. This is used in most of our video codecs, the way we're talking today. But let's say the ultimate consumer is actually a deep neural network or some other machine learning model in green. Then rather than look at the difference in the inputs, if you actually propagate this through a frozen deep neural network and look at the difference on the task space, so the outputs y hat and y, and use that to co-design or feedback how you learn the compression scheme, it turns out that you can get very aggressive compression ratios, but still not sacrifice on sensing task accuracy. So we've tested this on a couple classification domains, Mars terrain classification, and even some fairly sophisticated neural networks. But I'll show an example from a very toy neural network, which is MNIST. And you can see that essentially the x-axis is the bottleneck link. So how much you're sending across the air, what is the dimension? And the y-axis is your task loss, so your accuracy, the opposite of the accuracy. And in blue is our co-design scheme. So this is a rate distortion trade-off in information theory. So with a very small dimension, you get very low accuracy by feeding back the task loss as your ultimate performance criterion. And what you would typically do today is in red, is a task agnostic scheme. So if you simply try to reconstruct the image and then pass it through a pre-trained deep neural network, you don't learn the features that the network is most sensitive to. And therefore, you need a much larger dimension in order to achieve fairly good accuracy. So we have a preprint available that I'm happy to share. And I'll just end with one last thing, with one last thought. You can actually transition this to model-based control. So there are many cases where network operators generate a huge amount of congestion data in a city and useful mobility patterns. For example, how people are moving in a city, what the demand is at different cell sites. And I actually worked in industry at a startup that did this kind of work. And oftentimes a question would be, could you sell this to external agents in a city, such as Uber, to do proactive route planning? So the way to formalize this is the network operator might have cell congestion patterns that are very large telemetry metrics, you want to take this exogenous input S, encode it and decode it, but rather than predict the root mean squared error for the time series, if you pass it through a model-based controller, so simple linear model predictive control to route how many cars Uber is going to allocate, or how much you say the network operator will balance IoT traffic with real-time traffic, you can calculate the sensitivity of the control cost J with respect to the forecast and use that to co-design the forecast representation. So we have a preprint online. We actually used real cell data from my advisor startup that I worked at. This is with Telstra, the Australian network operator. And essentially you can get these rate distortion trade-offs that I showed for the inference case. So this is the control cost J as a function of how much data you send across the air. And if you co-design the representation of the time series, knowing that the ultimate consumer is model-based control, you can learn what features the controller is most sensitive to. And our system here is in orange and green. You can get very optimal control costs compared to today's task agnostic schemes. So with that, I'm happy to take any questions and describe this more theoretical work in detail if you'd like. And thanks for your time.
Thank you, Sandeep. Great talk. Are there any questions?
Yeah, Sandeep, yeah, I'm just trying to unmute myself. Okay, can you hear me?
Yeah, I can.
And I still have the God rays. So, yeah, very interesting talk. Now, the thing I was wondering is you have this criterion for choosing the images to upload to the cloud, right? So to do the cloud-based training. Mm-hmm. When essentially you are, according to some measure, a little bit confused, right, about what is it that you're saying.
Yeah.
Right, if I understand correctly. Now, what if instead of choosing those images to upload based on when you're confused about what you're seeing, is there a way that you can make that decision when you're confused about what to do about it? Let me explain. So if you see something, it could be an excavator, could be a bulldozer, could be a big truck. At the end of the day, it's a big thing that you shouldn't hit and probably move slowly, right?
Yeah, exactly.
So, and in a sense, you also, the other part of the talk where you talk about like a task-based, thing, right? So in a sense, wouldn't it be more helpful to choose the images that give rise to some uncertainty in what to do, right, rather than what you see?
Yeah. So that's an excellent question. In fact, that's exactly what we're doing now. So we are kind of propagating this into a model-based controller. Right. And you say, what is the sensitivity of my control cost or the decisions I would take as a function of what I'm seeing from the learned perception side? If there's quite a high variance in the possible scenarios the controller could take, if I may take a decision that kind of makes me at the cusp of my actuation constraints, or I simply don't know what to do, then I should cache these images and potentially even query another robot or the cloud, which is the second half of my talk. So it's currently in progress.
Yeah. I could see the connection with the task-based, like part. Yeah. But then you would also have to train. So then on the cloud, you wouldn't train only the image classification, right? Network is also the the decision, action, the task network or something, right?
Yeah.
Or the control,
Yeah. So actually, some of this work was very preliminary where I used to use a lot of learning-based methods. Now where I'm moving more towards all control is model-based, but the perception side is learned, and perhaps you want to learn a set of waypoints.
Yeah, thank you very much. Very interesting.
Other questions?
So I have one question.
Sure.
Yeah, thanks for the interesting talk. in the reward function that you define for reinforcement learning. So for one part, you are maximizing the accuracy, and for the other ones, you minimize the computational cost.
Yeah.
So there is a trade-off between them. So how you balance these two terms? So
yes, actually, this is very linked to Emilio's question. So these alpha accuracy and beta costs, I'm saying they're up to the system designer in our preliminary work. So let's say you have a very bitrate constrained link, then your system's cost might matter a lot. And let's say this is a small, slow moving robot on the factory floor. Maybe I can sacrifice on accuracy, okay? Whereas a safety critical situation, I might want to choose alpha accuracy to be extremely high. And if I have a 5G wireless link, then maybe cost doesn't matter so much. But an ideal solution would not have a static alpha and beta. It would actually look at the end control decision that I would take and use that to dynamically change these alpha and betas based on the fidelity of control I'd want and a risk sensitive ratio. Now, that's an open problem how to do that. We've just touched upon it in our current work.
Okay, is it possible for if we define priority in some algorithms, actually given different tasks, and based on some task, which one has priority to the other one?
Yeah, that's one way to do it. And also, it can be systems defined. So based on how much you care about your wireless link utilization and so forth.
Okay.
Yeah, so actually, virtually, this was a somewhat old talk. Virtually everything I've sort of done in this year has been more slightly theoretically principled. So there are people who are training now neural networks that come with provable approximation guarantees. So if you compress the neural network, then you can say that some sort of pack bound about how close the compressed outputs will be to the original network. So you can actually analytically kind of get an estimate of the loss function here rather than learn it from data. And these alpha and betas, if you plug in to a model-based controller, you might be able to modulate them. So I have some preprints online for this, but there's still a decent amount of work to be done there.
Okay, thank you.
Yeah.
Is there any final question? If not, I think we can thank the speaker again. I think, Sandeep, you left your coordinates in case somebody wants to reach out for deeper questions.
Yeah. You can email me. My Stanford email should be there for a couple more months, and then I'll transition. Yeah.
Good luck for your start at UT Austin. And thank you very much for your talk.
Good luck.
Thank you. Yeah. And maybe I'll reach out to you guys. I know you guys are doing a lot on co-design. So maybe we could trade some papers and so forth.
Yeah, for sure. I was already planning on reaching out. Yeah.
Yeah. Thanks so much. It was really nice meeting you all.
Oh.
Thank you. You too. Bye-bye.
Bye.